Hey everyone, welcome back to Cam Room 5. In the previous video, we were doing the activation energy and the Boltzmann curve. We had some activation energy and catalyzed values. We put our graph based on the data that there was a single molecule having energy between 10 and 20, two molecules with energy between 21 and 30, three molecules with energies between 31 and 40, and similarly, there were more molecules with average energies and fewer molecules with very high energy. Another thing we noticed from the curve that it was a smooth curve based on bigger data. The area under the curve was proportion of particles. And based on this smooth curve, we could draw a line to see how many particles had energies. Like in this green region, you can see it is the proportion of particles which have the energy equal to or more than 40 joules. All the particles with more than 40 joules have been highlighted with the green region. Here you can see the particles which have energies higher than 60. So this is the proportion of molecules with energies more than or equal to 60 joules. Similarly, more than 70, more than 80, more than 90, and more than 100. You can notice that when we have the activation energy values, the region would tell you how many particles have energy more than 80 joules or how many particles have energy more than 60 joules. Now moving on, imagine if I were to plot another graph with particles at 10 degree higher temperature. Now I am focused on their energies if the temperature was 10 degrees more. So there was 0 particle with energy between 10 and 20, 1 particle with energy between 21 and 30, 2 particles with energies between 31 and 40, and so on. The table was completed. Like there are 6 particles with energies between 61 and 70 joules, 5 particles with energies between 71 and 80, and so on. When we plot their graph, we get this purple normal distribution curve. Now if you notice that the activation energy was 60 joules like last time, and if you notice the yellow curve, which was the curve with lower temperature, the area under the curve is smaller. But in the purple curve, the area is bigger. It means that at higher temperature, more proportion of particles have energy higher than 60. But in the yellow curve, less particles had energy higher than 60. Similarly, at 80 joule energy, the yellow curve still has lesser proportion, but the purple curve has more. Now this leads us to an important conclusion. That at T2, for example, T2 was 40 degree, for example, and let's suppose T1 was 30 degree. You can see that the overall graph is tilted towards the right. When we write the explanation, what do we say? We say that more particles have higher energies. So overall energy of particle is increasing. Activation is still the same. And we say, and more particles have energy more than and equal to activation energy, or for example you can say energy more than and equal to the catalyzed activation energy, EA catalyzed. Since these particles have energy more than or equal to even activation energy, so more particles collide in a successful way. They collide successfully to make the products. That is our main concern here in each second, because it's all about rate of reaction. Let's try it in past paper question. It says the Boltzmann distribution for 1 mole of a gas at temperature T is shown. Since they're talking about 1 mole of gas, the area under the curve is 1 mole because it shows proportion of particles. 1 mole of the gas, 1 mole of the same gas is added and the gas remains at temperature T. Now you have 2 moles of gas, right? So your temperature is same, the gas remains at temperature T. It means the particles have still same average energies. The average peak, the average value should be same. So average peak was the most probable energy. It's going to remain the same. So let's look at options where the most probable or most average energy remains the same. Option B is categorically wrong because the graph is tilted towards the right. Why do you have two different average energies? Your temperature is still the same. Option D is also wrong because why do you have two different average energies? Why is your graph moving towards the right if the temperature is same? Even in option C, your average energy, why should it decrease if the temperature is same? The correct answer is option A because average energy is still the same in both graphs. The graph 2 is a little has more particles. That is why it has higher area under the curve. You can see blue and yellow curves have the same average value. Moving on, the Boltzmann distribution for the hydrogenation of an alkene at a particular temperature in the absence of a catalyst is shown. Which row correctly describes the effects of adding nickel to the reaction vessel? It's a catalyst, so the activation energy decreases. So I'm pretty sure option A for apple, C for cat should be there. But I can also see that the shape of the Boltzmann distribution doesn't change. Only temperature or particles change the shape. Your activation energy should decrease, but the overall shape of the curve should not change. So C for Cato is the right answer. You can see here, if I draw the graph, in the presence of nickel, the activation energy decreases. First, there were less particles with energies qualifying, now there are more. The Boltzmann distribution curve for a gaseous mixture of ethene and hydrogen is shown. Nickel is an effective catalyst for the reaction that occurs. How does the diagram appear if the same reaction mixture is at a higher temperature? You can notice that the activation energy should be the same, but the graph would be tilted towards the right like this. Your average peak would go towards the right. You will have more average energies and overall more particles with higher energy. So the curve would change. A is wrong. The value of both EA and EA catalyzed decrease. That is wrong. The values of both E and EA increase. The activation energy is not changing. The values of EA catalyzed and EA remain the same. That is true. The activation energies remain the same. The curve changes. The Haber process is usually carried out at a temperature of approximately 400 degrees in the presence of a catalyst. Changing the temperature affects both the rate of production of ammonia and the yield of ammonia. The Boltzmann distribution for a mixture is shown here. Let's just jump to the question. Using the same axis, sketch a second curve to indicate Boltzmann distribution at higher temperature. Like I've said, at higher temperature, the curve goes towards the right. The peak slightly decreases and the average energy increases. So your peak would decrease, but in the first graph there was most particles had lower energy. You can see X energy, but in the red graph you can see the average energy, the peak energy would increase. So here most particles have Y energy and Y is more than X. So the graph is tilted towards the right. With reference to the Boltzmann distribution, state and explain the effect of increasing temperature. So state means just tell me that rate increases. That's it. Now explain it. In explanation you would say that in the beginning, you can see I'm highlighting it with yellow, smaller proportion of particles were there. So the proportion of particles with energy more than or equal to activation energy is less. But in the blue region, you can see that it has more coverage. It means the particles with energy more than or equal to activation energy. More coverage means more proportion. So you will say at higher temperature, the proportion of particles with energy more than or equal to activation energy increases. Now more particles qualify for the reaction. So more particles collide successfully to make products. I hope the overall idea is clear for you guys, and I think you guys would be prepared enough for any question which might be related to the Boltzmann distribution curve. Stay tuned, guys. Thanks.